Hello, everyone. I'm not sure if you have a habit of exercising early in the morning. Jogging for 30 minutes at 8 a.m. can really energize your day. Just like the electronic clock we previously developed, it accurately records the passage of time. Building on the functionality of electronic clock display and the ability to adjust the time via buttons, we can now begin to design and implement the alarm clock feature. Today, we will achieve the setting and adjustment functions of the alarm clock through 3 steps: hardware circuit design, program design, and simulation effect. First, let's look at the simulation circuit diagram. The hardware circuit is based on task 5 with an additional button added. P1.7 is connected to button K1, which is used to adjust the hour value. P1.6 is connected to button K2, which is used to adjust the minute value. These 2 buttons are connected to the external interrupt P3.2 of the microcontroller through an AND gate. When either button is pressed, the microcontroller can immediately respond to the interrupt and execute the function to increment the value by 1. Today, we have added a new button, K3, connected to port P3.3 of the external interrupt 1, which controls the alarm clock function. When using it, if K3 is pressed, the value shown on the display switches to the alarm clock time. Pressing it again switches back to the current time. The specific time setting for the alarm still uses buttons K1 and K2. Next, let's analyze the method of program design. We build upon task 5 by adding alarm clock settings. The program structure and variables used are similar to those in task 5. The program is divided into 5 parts. Part 1 is the main function. Part 2 is the initialization function. Part 3 is the interrupt function, as shown below. Part 4 is external interrupt function 0. Part 5 is external interrupt function 1. The new features are in the interrupt functions, which are quite lengthy. Unlike task 5, besides handling the changes and carry calculations for hour, minute, and second values, the interrupt functions also need to determine, based on the alarm setting flag, whether to write the alarm or current time values into the display buffer array. External interrupt 0 needs to adjust the alarm or current time according to the alarm flag. External interrupt 1 must set the alarm flag. Let's check the program in detail. During programming, new variables alarm_hour and alarm_minute are added to store the hour and minute values set for the alarm clock, respectively. The bit variable flag stores the indicator of whether the alarm button has been pressed. This is the T0 interrupt function, which triggers an interrupt every 5 milliseconds. The completion of the timing function is the same as in task 4's electronic clock. I will not go into detail about it again. The following new content has been added. Judgment is made based on the value of flag to determine whether it is the alarm time or the currently displayed time. If flag equals 0, then the 6 numerical display segments corresponding to the alarm's hours, minutes, and seconds are updated and written into the display buffer array. Otherwise, if the flag is 1, the 6 display segments of the current time are updated and written into the display buffer array. This is the initialization function. Note that 3 interrupts are used, and in the initialization function, their respective control bits should all be set to 1. This is the external interrupt 0 function. Here, we will focus on its functionality. First, the state of P1 is transferred to the variable value. If the value of the variable is 0xbf, it represents that the button K2 connected to P1.6 has been pressed. Then, the function to adjust the minutes is executed. Pay attention to the adjustment based on the value of flag. If flag equals 0, each press of button K2 increments the alarm minute value stored in the variable alarm_minute by 1. If flag equals 1, each press of button K2 increments the current minute value stored in the variable minute by 1. Similarly, if the variable value is 0x7f, it indicates that the button K1 connected to P1.7 has been pressed, triggering the hour adjustment function. If flag equals 0, each press of button K1 increments the alarm hour value stored in the variable alarm_hour by 1. If flag equals 1, increment the current hour value stored in the variable hour by 1. This is the external interrupt 1 function. Each time button K3 is pressed, the flag is toggled. This represents switching between setting the alarm values and setting the current displayed time values. Let's add a piece of knowledge here, the bitwise NOT operation. Similar to the NOT logic gate discussed in the last lesson, this symbol represents a NOT operation, which involves flipping each bit within an X byte, combining the results into an overall result Y, as shown in the diagram. In this example, the bitwise NOT operation is used to determine the alarm button status. After the simulation begins, the initial value displayed is 23 hours 58 minutes and 52 seconds, and the second value changes once every second, which is the time change function of the electronic clock. Now let's check the button functions. Pressing K3 shows the alarm value on the display as 6:30. Pressing K2 adjusts the current alarm minute values to 31, 32, and 33. Pressing K1 adjusts the current alarm hour values to 7 and 8. Pressing it again shows the current time on the display. Pressing K2 adjusts the current minute value, and pressing K1 adjusts the current hour value. In this lesson, we have primarily learned how to enhance the electronic clock with an alarm setting feature through external interruptions and bitwise NOT operations. The control program is quite extensive, so you should review it several times after class to facilitate understanding and application. In the next lesson, we will attempt to add an alert sound to the alarm clock. You can start thinking about how you would implement this feature. To conclude, here are a few exercises to test your understanding. That's it for this lesson. Goodbye, everyone.